All right, welcome back to our flipped chemistry classroom. And today we are talking about acids, bases, and pH. So we explored a little bit of acids and bases already, and we've talked a little bit about what we already know. So this is really just kind of a review of what we learned today as we explored acids and bases. So there's sort of three basic models for acids and bases, or three definitions of acids and bases. So the first one, and the narrowest one, the earliest one, is the Arrhenius model. And so under the Arrhenius model, we know that acids produce hydrogen ions in aqueous solutions, and bases produce hydroxide ions in aqueous solutions. So this is a very narrow definition. It requires that it be in solution. It also requires hydrogen ions and hydroxide ions. But this is sort of the foundation of our pH scale, and it's a solid definition. Then as we grew to understand a little bit more about what acids and bases are and how they interact, we developed the Brønsted-Lowry model. And so the Brønsted-Lowry model broadens it out, and it says acids are proton donors. So we're still talking about hydrogen ions, but we've moved away from having to be in an aqueous solution. So we still have the idea that acids have hydrogen ions or protons. But now we've moved away from having to have hydroxide ions, and instead we're saying that bases are proton acceptors. So in the Brønsted-Lowry model, which quite honestly is the one that we'll use the most, acids are proton donors and bases are proton acceptors. And then the broadest model, the broadest definition, is what we call the Lewis acid model. And you might remember Lewis from Lewis dot structures. And so the Lewis acid model is all about electron pairs. And so the Lewis acid model says that acids are electron pair acceptors. So acids keep both electrons when the hydrogen leaves. So they're electron pair acceptors. And bases are electron pair donors. So bases have a lone pair that's available to be shared with that hydrogen ion or with something else. And so this is where the Lewis acid model broadens things out a little bit, in that we can have electron pair acceptors and electron pair donors, and we don't necessarily have to have hydrogen ions to define something as an acid or a base. And so we very often use the Lewis acid model with things like transition metal complexes, where we have acid behavior without having hydrogen ions. So as I said, the one that we're going to use most often is the Brønsted-Lowry model, and that's where we say that an acid is a proton donor and a base is a proton acceptor. So in order for a Brønsted-Lowry acid to be a proton donor, it has to have a removable proton. It has to have a hydrogen that is attached in such a way that it can fairly easily be removed. So generally speaking, this means that this is a hydrogen in a very polar bond. So very often hydrogen attached to oxygen in such a way that it's easy to break that bond and have it donate that proton. And a Brønsted-Lowry base has to have a pair of non-bonding electrons so that it can accept that hydrogen and form a bond with it. So if we look at our example here of hydrochloric acid and ammonia, we can see that when the hydrochloric acid reacts with the ammonia, that the bond between hydrogen and the chlorine breaks, and we get a hydrogen ion that then forms a bond with this lone pair that's on the nitrogen of the ammonia molecule. And we wind up with the chloride ion and an ammonium ion. Okay, so we talked about conjugate acids and bases. So a conjugate acid and base pair is where we are still applying this Brønsted-Lowry model, and we are saying, okay, if this is the pair, if one is the acid, what would be its conjugate base? So if we look at this sulfurous acid, H2SO3, it's behaving as an acid. And so when it behaves as an acid, it's going to give away a hydrogen ion. So the conjugate base, so that acid without a hydrogen ion, is going to be HSO3 -1. Now, this next one is a little bit more challenging. If we take a look at this potassium hydrogen phthalate, or potassium dihydrogen phosphate, we can see that we have this K at the beginning, and we don't normally have that in an acid, but we definitely don't have OH, so we don't have a base either. So this H2PO4, what is this? So when we think about this dissociating, it's going to give us a potassium ion, and it's going to give this dihydrogen phosphate ion. And the dihydrogen phosphate ion with a -1 charge can actually behave as an acid or as a base, because those two hydrogens are both removable protons, but it also can accept a hydrogen from something else. So if our dihydrogen phosphate behaves like an acid, its conjugate base would be hydrogen phosphate with a -2 charge. But if it behaves as a base, then its conjugate acid would be H3PO4. And so the difference between an acid and its conjugate base is just one hydrogen ion being removed from the acid, and so the base has one fewer hydrogen ions. The difference between the base and the acid is that the acid has one more. So if we look at NH3, its conjugate, if it's behaving as a base, as a proton acceptor, its conjugate acid is NH4+, or the ammonium ion. But if NH3 is behaving as an acid, then its conjugate base is NH2-. Okay, so when we put acids into water, they're covalent compounds, but they have a very unique characteristic. And that is that when we put an acid into water, it dissociates in the same way that an ionic compound dissociates, even though it's not an ionic compound. So strong acids dissociate completely. So when I put a strong acid into water, so this HA, it's going to dissociate, and it's going to give me one hydrogen ion, and then it's going to give me the anion, which we're going to call a conjugate base. Strong ions dissociate completely. When I put them in water, I don't have any more HA. I just have hydrogen ion and the anion, the conjugate base. Weak acids only dissociate part way. So we would still have some acid, but we would also have some hydrogen ion and some conjugate base. So we have to know 7 strong acids. Unfortunately, there's nothing for it but to memorize these guys. So there are 7 strong acids. There's 3 that are pretty easy to remember. These 3 here in the middle. The hydrogen iodide, the hydrogen bromide, the hydrogen chloride, or hydroiodic, hydrobromic, and hydrochloric acids. These are the binary halo acids. So these are binary acids with halogen ions, halides. So hydroiodic, hydrobromic, hydrochloric. Notice that hydrofluoric is not a strong acid, okay? And then we have 4 more. Perchloric, HClO4, chloric, HClO3, nitric, which is HNO3, and sulfuric, which is H2SO4. Those are the 7 strong acids, 3 binary halo acids, chloric, perchloric, nitric, and sulfuric. We have to know those 7. And that pretty much addresses our acids and bases. And I look forward to seeing you in class and answering any questions.